Hi, everybody. Let's take a look at part one, or I should say part A of the final exam, spring 2026. All right, I've built a circuit already here. Let's take a look at what we got, though. Kind of describe how to build it. I'm For part A, we're looking at what they call a coupling circuit. I'm looking at step two, kind of starting with step two here. Okay, I've got a source here, an AC source. This is a V sign or VSIN source. Okay, that's what you want to use typically in PSpice when you're simulating an AC source. There's also VAC, but you have limited settings with that. So this is the one we want to use. We want to use V sign for this, and you'll build this on your own. Okay, I've got an offset here of 2 volts. What that means, this is like having an AC source in series with a 2-volt DC source. That offset just shifts. It shifts up the um, the sine wave. So the sine wave we're going to generate here is riding on 2 volts DC. It's not riding on 0 volts. It's riding on 2 volts DC. And you set that with this offset. Okay, so we've got the offset set here. Okay, we said we wanted 1 volt RMS. 1 volt RMS, if you do the conversion, that's 1.414 volts peak or V amp. So that's our amplitude. Okay, we want a frequency for this one of 10 kilohertz. That's set to 10 kilohertz. We leave the AC blank here. Okay, we're defining some nodes in the lab, okay, or the final lab. VT is this node here, okay. We're going to look at the voltage drop across the capacitor and the voltage drop across the resistor, okay. So I've labeled them as VC and VR here. Okay, this RS is a source voltage. It's like built in. It's built into the source here. So it's like the voltage of a signal generator or I'm sorry, a resistance, a source resistance of a signal generator. I've got it set to 50 ohms. You can make that smaller or a little bigger, but not much so. 50 is typically what's used for source resistances. We got a zero point 0.1 microfarad capacitor here, and we've got a 20 k ohm resistor here. So this is our circuit, and we got ground over here. All right. So what do we want to do? We got this thing built. I'm going to I've already created a simulation profile. I'm just going to go in and edit what I have here. All right, we want to look at DC first. So I'm going to switch this to bias point. I'm on step 3. Okay. Um, I'm going to say apply and okay. I could have just clicked okay. If you click okay, it also does apply. I'm in the habit of clicking apply it and go okay. And let's run it. So again, we got a DC 2-volt source in series with a 1.414 volt AC source running through this circuit here in a clockwise direction. Let's look at what we got for voltages. All right, I hope this makes sense. Okay, we're just looking at DC. Just by clicking this little V up here, we're just looking at DC. Okay, we got 2 volts here. VT, that's what we should have since we've got an offset of 2 volts here on the source. 2 volts DC here. Okay, a capacitor looks like an open circuit. Okay, we know capacitive reactance is 1 over 2 pi FC. Frequency here is 0. We're talking DC. So it's for a DC source. We're just looking at the battery here. So for a DC source, the frequency is 0. All right, we're just looking at DC. That's what these, by clicking this little V up here, that's what these maroon or red uh, highlighted values are. 2 volts DC here, 0 volts DC here. DC frequency is 0. 1 over 2 pi FC. 1 divided by 0 is infinity or open circuit. So the cap under DC conditions looks like an open circuit. All right, so we got 0 volts here. We got 0 volts dropped across the resistor, and we got 0 volts on the node here. So it kind of your first set of calculations. Okay. Um, Let's turn off, again, click this V. These are just DC voltages. We haven't looked at AC yet. Now I'm going to turn this off. And I'm going to go back into my simulation profile. I'm on step 4. Okay, create a second simulation profile. We want to go back to a time domain or a transient response now because we want to look at AC. We want to run it out to 1 millisecond or microsecond. No, 1 millisecond. We want to run it to maximum step size of 1 microsecond. Okay, and we're going to put some probes in. Okay, I'm on again step 4. We want to plot VT. I'll click apply and OK here. So I'm going to grab a probe. I'm going to grab a single probe here, attach it here. Okay, this is to measure VT. This is going to measure, because it's a single probe, it's going to measure with reference to ground. Now, to get the voltage across the capacitor and the resistor, we're going to use this double set of probes here, this voltage differentiator markers. Let's go across the cap first. We'll look at VC here and here. See when I click it? Um, I get 2 sets of probes. Okay, let's do it again. Go across the resistor now. We're going to go here and here. All right. So we've got our probes in place. I'm going to run this now. Basically, I'm going to turn the circuit on. Okay, these probes are grayed out. They're just placed, but once we run the circuit, these will change colors, and you'll see here. So let's run it. Okay, so we've got VT is green, VC is red. This is the voltage drop across the capacitor, and we've got purple voltage drop across the resistor. That's VR. And let's take a look at our plot. What do we got? We said green was VT. That makes sense. If we look at our circuit, okay, you can see VT is going to be the way we've got the green probe here placed to measure VT. We're looking at both the DC and the AC portion of what's coming out of that signal generator. So we've got our AC signal riding on 2 volts. All right, riding on 2 volts DC. We get on the other side of the capacitor though. Well, capacitor looks like, what's going on here? That capacitor looks like a short circuit, doesn't it? We'll take a look at that in a minute when it comes to AC. All right. So we get to the other side. What do we got? The cap is blocking DC. So if we look at across the resistor, what do we got? We got the voltage, the sine wave VR riding on 0 volts, because that cap under AC conditions, under the conditions we have, looks like a short circuit at a frequency of 10 kilohertz. That's interesting. So you see this concept used. This is used in amplifier circuits. If you are an electrical engineering major, um, capacitors are used all over the place in transistor type circuits and semiconductors. For this reason, they can block DC and they will pass AC depending on how you have your circuit set up. And that's kind of what we're seeing here. All right. So I'm going to click back here. Let's minimize this. And we're going to jump to step 5, where we say, okay, let's change the frequency. Let's change the frequency to 1 kilohertz. I'm going to say, okay. And we really don't have to run it again, but I'm going to click run again anyways. Okay, we ran it. What do we get? Oops. You can see we're getting a little bit of a bump. We're starting to see some voltage dropping across, AC voltage dropping across the capacitor. Okay. So what's going on here? You're going to have to answer this, but I'll give you a hint. Okay. Remember, capacitive reactance is 1 over 2 pi f c. And what you're doing, if what we did was we changed the frequency from 10 kilohertz to 1 kilohertz. Okay. So what does that mean? You decrease the denominator by a factor of 10. Your x of c, 1 over 2 pi f c, is going to rise by a factor of 10. So the capacitor no longer is approximated at 1 kilohertz frequency as maybe as a short. So I don't think of it that way. I hope that makes sense. All right, I'm going to stop this. You're going to do part B on your own, and we'll see how you do. And make sure you ask me any questions. If you have any questions, I'd like you to spend some time on this.